In this lecture, we're going to begin by talking about some physics in the real world. String theory, as I emphasize, is not yet science. It's not yet physics. It's mathematics. But the peculiar thing about this mathematics is that it looks like the mathematics that we use to describe the real world. And so in some ways, it is mathematics that's inspired by the science that we know, and it actually begins to make predictions that are things that ultimately we will want to test, but it's not there yet. So we're going to go back in time for the beginning of today's lecture to the year 1861. In that year, a young Scottish physicist by the name of James Clerk Maxwell produced the first color photograph. Now that surprises lots of people because most often people think that color photography is a new development. But in fact, this young man had the capabilities and the technology to do this at that point in time. What's really more interesting in the story, however, is that he first figured out how we see color, and that's how he was able to produce the technology. Maxwell was the physicist upon whose shoulders Einstein most clearly stood in producing the theory of special relativity. Maxwell's 1873 paper entitled A Treatise on Electricity and Magnetism contains 4 equations, and from this equations humanity was led to an understanding of what is light. The equations tell us that light is an electromagnetic wave propagating. No one had ever thought of such possibilities before, and in order for this to happen, we need to have electric and magnetic fields that change as they move through both space and time. They play, in fact, a sort of a game of leapfrog. First, there's a little bit of electrical field that has to change in space and time. That generates a magnetic field, which then must change in space and time. Next to electric field, and this happens over and over again at a certain speed. In fact, the speed is the speed of light. So this was Maxwell's great discovery, and all of our new high technology, all of our communications technology, in fact, can be traced back to these 4 equations. Sometimes in talking to the public, I call these equations the DNA of modern information technology because they contain the instructions for how we build things like radios and televisions and what have you. Now, Maxwell's predictions started off as a piece of mathematics because remember I said there were 4 equations that he wrote. The way mathematics gets turned into science is that someone tries to falsify the equations. Science is really not about truths. That's what people often say is the notion of truth in science. But in fact, science is about finding beliefs that are less false. So when someone asserts that an equation applies to their world, what you try to do is prove that it doesn't. This was done in 1888 by a German physicist by the name of Heinrich Hertz, who actually built an experimental device and detected these waves of electromagnetic energy that were predicted by the equations. Oh yeah, Hertz, as in megahertz. That's where we get the expression from it. The Hertz in the word megahertz is tribute to the work of this physicist. Now, interestingly enough, after Maxwell's great triumph of discovering these equations, he tried to describe gravity. Wow, think of that. You know, this guy just figures out how electricity and magnetism works and then immediately sets the goal for gravity. And unfortunately, in an echo of Einstein's experience, he also failed. But roughly speaking, his attempt occurred about 50 years before Einstein tried to take his theory of gravity and combine it with electromagnetism. So in some sense, the two of them are wonderful bookends in history that both tried to achieve the same goal, but from 2 different points, and both failed. Now, in the description of the photon, I said they have to change in space and time. Let's talk about change a little bit. And for this purpose, I have a video. We've seen this video before. This is the one where we talk about how an invariance occurs when you can take a right triangle and look at the respective areas on the side. Well, when you look at the picture here, it's still, but we can put it in motion, and now we can see changes. In fact, we see a change in the area as the blue area gets smaller, the brown area gets larger, but they do so in such a way that the sum of the 2 is always the green area. So that's the whole notion of change. But let's talk about change in a slightly different way. This illustration is supposed to be 2 bowls of ping pong balls. And as you can see, the two bowls are different in terms of how many ping pong balls are in them. One has clearly more ping pong balls than the other. The one on the left is fuller than the one on the right. And now let's induce a change. The change is that we're going to take ping pong balls out of each bowl. So here we go. But you'll notice that what happens is that even though the bowls are filled to different capacities, the number of balls that go out was actually the same. So this is actually a very interesting idea because it says that you can take two things that are actually different, but the change in them can be the same. Now, the reason this is a very important idea is because this is what Maxwell's equations tell us about the relationship between electricity and magnetism, which is something that we can measure in the laboratory, and these things that we're called photons. Remember, we've talked about the quantum of the electromagnetic field, the thing that is the message carrier for the electromagnetic force of the photon. Well, what Maxwell's equation tells us is that it is actually the change in the photon that produces the electric and magnetic fields. The equations are even more remarkable because what they also tell us is that if there is no change in the photon, then you don't actually produce electromagnetism. Now, our example of the two bowls have a very important lesson because what they tell us is that it's possible to have two photons where each of them experiences the same change, even though they're different, but because the electric and magnetic fields are produced by the changes, not by the photons themselves, the two photons are indistinguishable. This is a very important idea in physics. In fact, it is so important that it gets a special name. We call it gauge invariance. The fact that it's the change in photons that produce the things that are physically measurable, not the photons themselves. Now, this idea that the change is what's responsible produces for us a very interesting result because suppose we imagine that we have photons in a box. Well, you can actually do that. Build a box that has mirrors on the inside and shine a light beam in there. It's full of photons. So what we want to do is ask a very simple question. How much energy is in a box caused by the photons? Well, that's an interesting question because we know that for a given E and M field, which are what causes charges to move or would bend a magnet if we were to put it in a box, we know that for a given E field, more than one photon can produce that. Well, that's interesting because we can imagine two boxes where the electric and magnetic fields are the same, but the photons are different, but their changes are the same. That's the important message. We can go on to the question of energy. It turns out that the energy that's in each box actually depends on the photons. But now we have a puzzle because since it's actually the change in the photons that produce the energy, the electric fields, and it's the electric fields that we can measure, then we cannot, in fact, directly measure the photons. And that leads to a very important principle. It's called charge conservation. The fact that you cannot directly tell which photon produces how much energy is the result that leads to charge conservation. This was actually first understood by the mathematician by the name of Emmy Noether. In fact, there's a very great result in mathematical physics that's called the Noether theorem. What it tells us is that if you have some quantity that changes, but that physically measurable quantities don't depend on those changes, then there must be conserved currents. Well, let's stop and think about this for the photon. We're talking about these changes, and we know that we can't quite measure photons directly. We can only measure the change in them. So what's the conserved quantity associated with that? Well, remarkably enough, it's electric charge. You probably heard in your science class that charge is a conserved quantity. Well, it is. But it turns out that because of Noether's theorem, we understand that the conservation of electric charge is actually a lesson about the ability of two different photons to produce the same electric or magnetic field. So, we've learned a very great lesson here that it's not in physics always the quantity that's of interest. Sometimes it's the change in a quantity that's of physical interest. So now, let's talk about the fact that our world is quantum mechanical. Remember, we have in previous lectures actually gone down in size, leaving our world and going down to the world of what I call the denizens of the quantum world, the quarks, the leptons, the photons, the intermediate vector bosons, the force carriers. Those were the denizens we met. In their world, the laws of motion are very different from the laws of motion in our world. Now, that has an important implication for charge. And in order to show this implication, I have another image that would be useful. Here's a bowl. And as you can see, there's a ball that's on the side of the bowl. And now what we're going to do is to watch what happens as we put this in motion. We're going to let the ball roll down into the interior of the bowl. You'll notice there's a hole down there. And so it rolls down and falls through the hole. If we put a second ball in the same place, it does exactly the same thing along exactly the same path. We put a third ball there, it does the same thing. Now, the fact that all of these balls do the same thing if you put them in one place is a result of classical physics. Classical physics says that if you put an object in a certain position in the same way, it will always follow the same path, and that's what we see in this idea. Now, imagine these balls are actually charged objects. Then what this is a picture of is a conduction of current. And we can see that all the amount of current we put in, that is putting the balls to the side of the bowl, goes out the bottom. So all the current in is equal to all the current out. That's actually charge conservation. That's what we physicists mean by charge conservation. Okay, so that's how charge conservation works at the classical level, at the level in which we're used to looking at our world. But remember, in the quantum world, things are different. So let's go and visit the quantum world and ask about the same experiment. Here again, we see our bowl with, this time we're going to put several balls on the lip of the bowl. Watch what happens as they roll down into the middle. Well, as you can see, they don't all travel along the same path. In fact, they can travel along different paths. Now, why is that? Well, let's remember how the quantum world actually works. In the quantum world, we cannot say with definite precision what exactly happens between the time we observe something at one time and observe it at a later time. So let's go through this again and see if we can figure out what's going on with our balls. So we would observe the ball when we put it on the lip, and then as it moves down towards the hole, it can take many different paths. In my illustration here, I have a green ball, a white ball, and a red ball. And they sort of some of them wander around as they try to make their way towards the hole at the bottom of the bowl. This wandering, that's quantum mechanics at work. Because even though we put the balls in the same place at the same time, according to the laws of quantum mechanics, they're allowed to wander around in trying to reach the bottom. And so now we can see the wandering. Some of them go to one side, some to the other. Eventually, all of them go out the bottom of the hole. Now that contains an important lesson. Even though the laws of motion are different in the quantum world, as long as all the balls that are placed on the lip of the bowl get out the bottom, charge is still conserved, even though the world is quantum mechanical with all the wandering in the middle. Well, is that the only outcome that's possible? Well, the answer, interestingly enough, turns out to be no. There's one other outcome which is actually very startling. So since the balls can wander, what would happen if we put a number of balls on the same place, one after the other, and watch them wander? But suppose some of them never wandered out of the hole in the bottom. We put them in the top, but they didn't get out the bottom. What would that mean? Well, since it's actually the putting for every ball that you put in the top must go out the bottom, that's what we mean by charge conservation. If some of the balls never get to the bottom, it means charge is not conserved. This is such a startling result that even physicists had a hard time accepting this. This was actually first discovered in the 1950s, that in a quantum mechanical universe, if you watch how charge propagates, sometimes it is not conserved. So here we see an example where if we watch our balls, instead of all of them going down to the middle and going out of the hole, some of them just wander around the bowl forever and never go out the bottom of the hole. That's what physicists call an anomaly. Now, all of the things I've just told you are properties of our world, and we have mathematical descriptions to describe these things. So now, we want to take some of these properties and put them into our picture of string theory. So how shall we do this? Well, we've learned about anomalies. We've learned about the fact that sometimes things that are physically measurable are actually related to changes as opposed to being directly related to the objects present. When anomalies was first discovered, as I said a moment ago, even physicists had a hard time accepting that. In fact, there's a story. Let me tell you a story about this. Supposedly, there was a graduate student who made a calculation and found that when he did the calculation one way, he saw charge conservation. He did the calculation a slightly different way. He concluded that charge was not conserved. At first, because of this, he was convinced that he had made an error in the calculation. So he checked the first method of calculation, found out again that charge was conserved, checked the second method of calculation, found out that charge was not conserved. And this young student, who had hoped to become a theoretical physicist, concluded that whatever was going on with his calculations, he wasn't wrong, and he became an experimental physicist instead of a theorist. Now, I don't know if the story is true, but one often hears this story about the discovery of anomalies and what it has done. So, anomalies are truly bad news. Why? Well, you see, if charge is not conserved, then it means that the changes in the photons actually have relevance. But if that the part of the photon that doesn't change has relevance. But if that's true, then there's a part of the photon, at least for the mathematical description of the photon, which is an object we physicists call a time-like particle. Now, that name may not scare you, but the only problem is time-like particles act like tachyon. And in our discussion, we have seen that tachyon has the power to destroy physics. It renders all of our predictions nonsensical. Time-like particles have exactly this same property, even though technically they're slightly different from tachyon. So, if you have a theory with anomalies, it turns out that is a theory that makes no predictions about the real world. Now, the interesting thing about anomalies and tachyons is that the anomaly doesn't just have to apply to the force carrier for the electromagnetic field. Any kind of force carrier, potentially, when you look at it at the world of the quantum, the world where the denizens run around, any kind of force carrier might have an anomaly. The presence or absence of anomalies was worked out by three physicists, Adler, Bell, and Jacques. They gave the mathematical criteria which basically said that for every ball that you put at the top of the bowl, it goes out the bottom. That's when charge is conserved. But they also found out what conditions had to be satisfied when you put a ball at the top and repeatedly do that, and find some of them that wander around in the bowl and never go out the bottom. It's called the Adler-Bell-Jacques theorem. It can apply to mass and energy, because Einstein's great discovery was that energy and mass are the same thing. It can apply to the other forces in nature, not just electromagnetism. We've talked about the two forms of nuclear energy, the strong interaction and the weak interaction. Each of these can be subjected to anomalies. And if an anomaly occurs, time-like particles appear for all the force carriers, totally destroying the quantum world and our ability to make calculations. Well, the thing that's really interesting, because this so far has been a story about our world, is that the mathematics of anomalies actually occurs in string theory. You remember, string theory is really, it's a mathematical construct. It tells us that at very small levels, at the very tiniest levels, our universe looks like it's somehow constructed by little pieces of pasta, little filaments. The mathematics of that is what we string theorists actually study. We study how these things are described in terms of their mathematics. And it turns out that, as we've discussed, when a string vibrates, that vibration is too small to actually produce sound. So instead, the vibration from our level appears to be a particle. So, if that's the case, then it means that all of the force carriers that we know in our world, which are actually, from this point of view, vibrations of the string, it means that if each of these force carriers or any of them acquire anomalies, then the string itself must be subjected to anomalies. So, if the string is subjected to anomalies, what does that actually do? Well, just as anomalies destroy our ability in the real world to make predictions, the presence of an anomaly in the mathematical world of the string has precisely the same effect. We find that objects that are very similar to tachyon appear. We know that the effect of tachyon, or the tachyon more properly, is that it destroys the notion of probabilities. Time-like particles do exactly the same thing. You get a mathematical description where probabilities can be greater than 1 or less than 0. And of course, we have no way to interpret such a thing. So let's now pick up the story about strings, because around 1982, a marvelous discovery was made. We talked about the fact that strings come in several different varieties, and when you add spin to strings and put a certain restriction that says that you want equal numbers of fermions and bosons to appear in the oscillatory patterns, you get a property called supersymmetry. Well, in 1982, two physicists, John Schwartz and Michael Green, actually worked this out for the first time, how to see supersymmetry and use it to permanently banish tachyon. They actually did more than that, because they also started to ask the question, can we incorporate forces that are like the electromagnetic force, that are similar to the weak and strong nuclear forces? And they found out in their mathematical world that yes, they could actually do that also. But this mathematical world is a world that's quantum, that is in the quantum regime, and therefore might be subject to anomalies. In 1982, while in Aspen, there's a physics center in the city of Aspen where typically for the last 20 years you can find some of the countries and the world's most active physicists working feverishly to derive new results. Well, in 82, Michael and John were there, and they studied the question about whether this idea of anomalies had anything to do with the forces and the force carriers that they had constructed for the so-called superstring. What they found was quite remarkable. All of the forces, as we've talked about, have force carriers, and all the forces also have charges associated with them. With the electrical forces, the electrical charge. For the strong nuclear force, we call that the color charge. For the weak nuclear force, we call that the weak charge. So every single force is always associated with a charge. You might wonder what's the charge for gravity? Well, it's actually Newton's constant. So every charge is associated with this force. Now, if you have many, many forces, it means you've got to have lots and lots of charge. So in 1982, Green and Schwartz did a calculation very similar to our bowl analogy. They looked at the mathematics and the theory, they started putting little balls in, and then they figured out which theories have the property that all the balls that you put in the top of the bowl get to the bottom. What they found out was that only two such mathematical constructs exist. In one of these constructs, they found that you need exactly 496 charges. Where in the world would you get such a number from? 496 charges. Well, since string theory is about mathematics, and since by now those of you who have been listening to me have actually, in some sense, peeked into PhD level training for mathematics, we can explain this number 496. Remember, when we go back to talk about our areas, and we'll do that one more time, bring that back because it's a very useful concept. When we talked about our areas and the invariance, we could do it in two dimensions, where the statement was that the green area is always equal to the sum of the blue plus the brown. And that's true no matter how we orient the two areas. So we can make the brown area larger, we can make it smaller, but the sum of the two is always the same. Or we could do something else. We could actually take the areas and construct a third one, which was, as we can see here, in terms of my ladder, it means I've tilted the ladder over. Now, each of these areas can be sort of thought of like charge, at least in the context of the calculation that Green and Schwartz did. And so, how do you get the number 496? Well, the answer turns out mathematically to be the following. You see, in our world, we can do rotations. So I can rotate like this. That's what we physicists like to call a rotation about the z-axis, because z is up for us physicists. Or if I hold my hand like this and did a backflip, I would rotate about my arm. That would be a rotation about the x-axis. Or I could hold this arm out at 90 degrees with respect to the first arm and once again do a backflip. That's what we would call a rotation about the y-axis. So in our world, there are three basic rotations. In the world of the string, one way to get the number of 496 is to consider a world in which there are exactly 32 ways in which to rotate. Because this number 496 is the number of rotations that you could construct if the world had 32 directions. So, for this reason, the string that Green and Schwartz found in 1982 was called the SO32 string, because it's a way to understand where this number 496 comes from. Why is it magically that for 496 charges, all of them make to the bottom of the bowl? Whereas if you pick any other number, you always have an anomaly. If you have an anomaly, you get time-like particles. If you get time-like particles, that destroys probabilities. And so only for this magical number of 496 do you get a piece of mathematics that you can use to make predictions about our world. This was the real birth of superstring theory. And in 1982, it became clear that the goal of Einstein was within our grasp. Now, what was this great goal of Einstein? Well, early in this lecture, I talked about the fact that both Maxwell and Einstein actually tried to do the same thing, but from two different points. Maxwell wrote the equations that described electricity and magnetism, and after they were successfully written, he wanted to include gravity. Einstein, on the other hand, as we've learned in a previous lecture, wrote the equations that describe gravity. And after he was successful, he wanted to modify those equations to include electricity and magnetism. So both of them wanted to do the same thing. And both of them failed. In Einstein's case, after a 30-year-long search, the last 30 years of his life, he still did not have this single description of both gravity and electricity. Well, the work of 1982 made it clear that we could grasp this thing, that we were almost at the goal of Einstein, because this magical 496 that I was talking about was in the context of a string theory. Now, the difference about a string theory is if it's one of the closed strings, one of the ones that looks like a little hoop that we've seen in previous animations, all such theories necessarily describe gravity. On the other hand, the string is capable of vibrating in many different ways, and one of its other ways of vibrating describes the force carriers that are associated with things like electromagnetism. So, if you could find a theory that had in its mathematical structure the description of photons as well as the description of gravity, then you have succeeded where both Maxwell and Einstein failed. So, it was clear that it was within grasp, and when the SO32 string was completed, that grasp became not a potentiality, but an actuality. The world's first unified field theory was born in 1982 with the work of Green and Schwartz and the construction of the SO32 string. Now, this was a source of great joy in the physics community because it meant that this 30-year-long quest of Einstein had been fulfilled. By the end of Einstein's life, most of the physics community sort of thought of him as kind of passé, someone who was off on some journey that had no useful purpose to physics. Very few people, by the end of Einstein's life, followed his quest for the unified field. Einstein died in 1955. It was 1984, some 29 years later, when his dream was realized in Aspen, Colorado.